Welcome everyone to the Spectral Geometry in the Clouds seminar. Today we have the pleasure of having James Bonifacio from Cambridge, and he will speak about bootstrap bounds on closed hyperbolic surfaces. The virtual floor is yours.
Thank you. So yeah, thank you for the invitation. It's great to speak here. I've been following this series since earlier on in the pandemic, so it's nice to be here. So I should say I'm a theoretical physicist, but I'm interested in spectral geometry and some connections it has with physics. And that's part of the story that I'm going to talk about today. But you won't need to know any physics for this talk. And but please do ask questions, interrupt me if anything I say is unclear or I'm using unfamiliar terminology or anything like that. So my main goal here is to advertise this bootstrap approach for finding constraints on eigenvalues, and hopefully get you interested in this approach. So this talk will be mostly based on these two papers, these archive numbers here. And so these are about hyperbolic manifolds. But there was also this earlier paper that I wrote with Kurt Hinterbichler, which is about Einstein manifolds. And there was also this paper by some other authors, which came out on the same day as the most recent one of mine. So by Petr Kravjak, Dalamul Mazak, and Shredik Pau, and it has a lot of the same results, but they approach it from a more representation theoretic point of view. Let me tell you the outline of my talk. So I'll break it up into two parts. The first of which will be more of an overview, and then the second part will include some more details, and I'll also mention some other bootstrap results. So for the overview, I'll start by talking about hyperbolic surfaces and eigenvalues, and then tell you about these bootstrap bounds. So let's start with hyperbolic surfaces and eigenvalues. So as is customary in this kind of talk, I will begin by telling you that I'm going to have some manifold M equipped with a metric G hat, because I want to use G for the genus. And so this will be, in particular, a genus G surface, and the metric G hat will be a hyperbolic metric. So that means that it's a metric of constant negative sectional curvature. And so, for example, I can write the Riemann tensor in components in terms of the metric like this. So this constant kappa is the curvature, and I can normalize it to be -1. I'm also going to assume throughout that the surface is closed. So that means compact without boundary, that it is connected, and also orientable. With these assumptions, it's known then that hyperbolic metrics exist for the genus G greater than or equal to 2. So here are some examples of genus 2, 3, and 4. And in fact, on a genus G surface, there's a whole 6G minus 6 dimensional moduli space of hyperbolic structures, which means hyperbolic metrics up to diffeomorphisms. So on a hyperbolic surface, I want to, as usual, define the Laplace-Beltrami operator, or just the Laplacian delta. So acting on functions, I'm going to define this as just minus the divergence of the gradient of the function, so that it's non-negative. Then we're going to be interested in solving the eigenvalue equation with eigenfunctions phi I and eigenvalues lambda I. So we know that delta is strongly elliptic, it's non-negative, and on an appropriate domain, it's essentially self-adjoint. So this tells us, for example, that the eigenvalues are discrete, that they can accumulate only at infinity, and therefore I can order them like so. So I have the lambda 0 equals 0, which is the unique 0 eigenvalue, because I've assumed that the manifold is connected. Then there's some non-zero gap to the first non-zero eigenvalue lambda 1, which is also called the spectral gap. And then lambda 2 is greater than or equal to lambda 1, because I've listed them with multiplicity, and so on, all the way up to infinity. We also know that the eigenfunctions phi I are smooth by elliptic regularity. And by the spectral theorem, they form a basis for the square integrable or L2 functions on the manifold. Without loss of generality, I'm going to take them to always be real and orthonormal. Okay, so what do we know about these eigenvalues for hyperbolic surfaces? Well, there are no exact expressions for eigenvalues, as far as I know, on any hyperbolic surfaces, but you can find them approximately numerically. So, for example, we can use this so-called method of particular solutions, which is implemented in this Fortran program called HYPERMODES by Alexander Stromain-Wielewski. And using this program and some other ones, they, for example, computed to many decimal places the first 1,000 or so eigenvalues of the Bolza surface. So the Bolza surface is this genus 2 surface, which is the genus 2 surface with the largest symmetry group. And you can obtain it, for example, from a regular octagon here shown in the Poincare disk by identifying opposite sides. And so they found, for example, that the spectral gap of the Bolza surface is 3.8388873. Okay, another approach is to use the finite element method. So, for example, there's this open source software free FEM++, and this was nicely used in this thesis by Joseph Cook to compute eigenvalues for various surfaces with hyperbolic metrics. So, for example, he computed some of the eigenvalues for this genus 3 surface called the Klein quartic, and this is the surface of genus 3 with the largest symmetry group, and its spectral gap is roughly 2.678. And so I should say that these surfaces are also conjectured to have the largest values of the spectral gap for their respective genera. Numerically finding eigenvalues, we also, of course, like to prove general bounds on eigenvalues. So the first bound that I'm going to mention is the famous one from 1980 by Yang Yao, with this improvement pointed out by Al-Sufi and Ilias. And it tells you in the sort of strongest form that they prove in their paper that for hyperbolic metrics, the sum of the inverse of the first 3 non-zero eigenvalues is bounded from below by this function of the genus G, where this is the floor function. And so in particular, you can use this to derive the following upper bound on the spectral gap, lambda1. So lambda1 must be less than or equal to this function of the genus, which for G greater than or equal to 2 is less than or equal to 4. So the Yang-Yao bound applied for more general metrics, but this is what it shows with hyperbolic metrics. And okay, so this bound on the spectral gap can also be generalized to higher eigenvalues. So in this paper by this more recent paper by Kapukin, Nadarishvili, Penskoy, and Porterovich, they show that lambda k is less than or equal to this function of the genus in K. Okay, so the Yang-Yao bound gives for genus equal to 3 that the spectral gap must be less than or equal to 3. Quite recently, this was improved in this paper by Antonio Ross, and he showed that in fact lambda1 must be less than or equal to this number, which is roughly 2.708. And then subsequently, improved bounds were found for almost all other genera in this paper by Kapukin and Vinokurov. Let me also mention this famous lower bound by Otto Rosas, which is that the 2G minus 2th non-zero eigenvalue is at least a quarter. And there are also many other results on eigenvalues of hyperbolic surfaces, including by people in the audience, but these are the ones that I'm going to need for this talk. And I can summarize them. I can summarize the constraints on the first 2 non-zero eigenvalues with this plot that I've shown here. So here I've got the x-axis lambda1, on the y-axis lambda2, and these different colored regions show you the regions that are allowed by these various bounds that I just talked about. So this curved line is a bound on lambda2 that you can derive from the Yang-Yao bound. And so this blue region is genus 2, the orange region is genus 3, and the green region is genus 4. And I've also shown some examples. So this black dot is the Bolza surface. This is the Klein quartic. This one is Bring's surface. And this black line here is some particular 1-parameter family of genus 2 surfaces. And you'll see why I included this on the plot later on. But these eigenvalues were computed using this program HYPERMODES by Stromae and Wielewski. Okay, so this is sort of a pictorial summary of the some of these bounds on the first 2 non-zero eigenvalues. Now let me say something about these bootstrap bounds that are going to be the subject of this talk. So I'm going to talk about a way to find bounds using the so-called bootstrap approach. And as I mentioned earlier, there's also this other paper which explores this idea. And the two results that I'll focus on are for genus at least 2, you can use this bootstrap approach to find an upper bound on the spectral gap of genus G hyperbolic surfaces, which is that lambda 1 must be less than or equal to 3.8388977. And you should compare this to the value for the Bolza surface, 3.8388873. And in particular, you can see that the Bolza surface is almost saturating this bound to within 1 part in 10 to the -5. So that provides good evidence for this conjecture that the Bolza surface does in fact have the largest value of the spectral gap. Similarly, for genus 3, you can use this bootstrap approach to find an upper bound on the spectral gap of 2.678483. And again, this is quite close to the numerically computed value of the Klein quartic. So again, suggesting that this surface provides evidence that it maximizes the spectral gap in genus 3. So I should say that in my derivation of these bounds, I use numerical computations, which are strictly speaking non-rigorous because of the software that I use. But the types of computations involved are ones that you can make as rigorous as you like, following, for example, the approach by Korenalkis for sphere packing bounds, or in the seminar series a few weeks ago, there was a talk by Maxime using linear optimization. So if you use the appropriate software, you can make rigorous statements, and you would get the same values that I've quoted here. That's the expectation, and this was also partially done also in this other paper here. So you can trust the quoted bound to the precision that I've stated it.
Please.
Yes. Was that a question?
Yeah. In your first example, I think that lambda 1 depends on the domain.
I'm not sure I know what you mean. I'm on a closed surface. Is that does that resolve your question?
Population phi I equal lambda phi I. I don't see that. I think that lambda depends on domain.
So I guess I'm always including the whole manifold. I'm not looking at subsets of the manifold. Yeah, so I'll always be talking about the closed eigenvalue problem on the whole manifold.
Lambda 1 for the first example is the value is different. Then I think lambda is depend on the domain. But in the equation, I don't see the domain. My question is just here. I don't see the domain.
So I'm thinking of these phi I as the functions defined over the whole manifold, and it's closed. So there's no boundary, so it's just a closed eigenvalue problem, rather than restricting to subdomains of the manifold, which maybe is what you're thinking of. So here let me tell you what I mean when I say this word bootstrap. So this is some sort of general term that's thrown around a lot in different areas of physics and in maths. And the general philosophy is that you want to try and use some basic consistency conditions to try to constrain or even solve for some parameters of a system. So this is necessarily quite vague, and it comes from this expression to pull oneself up by one's own bootstraps, which historically has some connection to this picture that I've shown here. Concretely, what do I mean by this in this context of hyperbolic geometry? So let me tell you what I mean by consistency conditions. So this slide is telling you sort of where the non-trivial input is coming from. So the consistency conditions that I'm going to use come from using completeness and associativity to write quartic overlap integrals of eigenfunctions in terms of products of triple overlap integrals in 2 different ways. one of the main ideas. So let me give you an example of what I mean by this. So by completeness, I just mean the fact that, for example, I can expand the product of two eigenfunctions in terms of eigenfunctions, because this product is smooth and in particular L2. So I can decompose it in some L2 expansion in terms of eigenfunctions with some coefficients, C, I, J, K, which I've defined as the integral of the product of three eigenfunctions, I, J, K. And I'll call, this is what I mean by a triple overlap integral in this talk. And here I've separated out the non-zero eigen, or the non-constant eigenfunctions from the constant eigenfunction. Okay, so that's completeness. By associativity, I just mean the associativity of the product of eigenfunctions on the manifold. And I'm going to use this in a very particular form. Namely, I'm going to consider an integral of a product of derivatives of eigenfunctions, say. For example, here I take the integral of the product of the first derivative of the eigenfunction squared times the eigenfunction squared. And then I'm going to use completeness to write this in two different ways. So for example, I could take the first and the second terms. This is some function. I can expand it in terms of eigenfunctions, and I'll get the first term in square brackets that I've shown here. And then I can similarly expand the third and the fourth terms in terms of eigenfunctions, and I'll get the second term in square brackets here. And now this is quadratic in the eigenfunctions, so I can do the integral using orthonormality. And then what I'm left with is an infinite sum over products of these triple overlap integrals. So this is one way of rewriting this quadruple overlap integral. Now, I could have alternatively decided to take the first term and the third term, and similarly use completeness to write them in terms of eigenfunctions. So that would give me the term in square brackets, and similarly for the second and fourth term. And again, I can use orthonormality to do the integral, and I'm left with an infinite sum over squares of these triple overlap integrals C. And these have to give me the same result because they're just two different ways of computing the same integral, or rewriting the same integral. So what I end up with is this consistency condition that I've shown at the end here. So it tells me that some constant term, depending on the volume V, plus this infinite sum over squares of these triple overlap integrals with some prefactor, depending on the eigenvalues, must equal 0. So this is just some identity that has to be true. In fact, I haven't used the fact that the metric is hyperbolic anywhere. So this is an identity which is true on a general closed Riemannian manifold. And you can imagine now coming up with more complicated versions of these consistency conditions by, for example, inserting more derivatives in this quartic overlap integral, and by, instead of using eigenfunctions, using transverse traces, eigentensors, or eigenforms, or so on. You would get more complicated versions of these consistency conditions. Okay, so maybe this is a good point to pause just to make sure there are no questions.
So just a simple question. You're doing this coordinate system by coordinate system. You choose one particular one, or it's not relevant?
Yeah, it won't matter in the end. I'll do it in a sort of invariant notation later on. Okay. Yeah, I guess I don't actually have to compute anything. I'm just formally manipulating these expressions because I'm never committing to a particular hyperbolic metric. Okay, and let me maybe just point out this 3/4, and in the second half I'll come back to some generalization of this. Okay. So this, yeah, like I said before, this is sort of where the non-trivial input comes from. So you can imagine now deriving more complicated versions of these consistency conditions, but it's not immediately obvious how you can use these consistency conditions to learn anything useful about things we care about, such as low-lying eigenvalues, because they involve infinite sums over these triple overlap integrals, which a priori we don't really know that much about. And so this problem also arose in a area of physics called conformal field theory, where there were these consistency conditions, and for a long time it wasn't really known how to, in general, get useful information from them. But then there was this breakthrough in 2008 by these people, Rattazzi, Richkov, Tony, and Vici, these physicists, who found a way of getting useful information from these consistency conditions. And this is goes under the name the conformal bootstrap, or the modern conformal bootstrap. And so what we can do is basically import all of the technology that these physicists have come up with in order to solve this problem in this context, and apply it to these consistency conditions that we have for manifolds. So in our context, the procedure suggested by this conformal bootstrap approach is the following. So the first step is to postulate some candidate eigenvalues. You then try to find a contradiction with the consistency conditions. And this is a step that you can optimize numerically using, for example, semi-definite programming. And then if you're successful, you can conclude that the candidate eigenvalues are inconsistent. So you're thinking of these consistency conditions as being like an oracle to which you can pose questions of the form, is this spectrum of eigenvalues consistent? And the oracle can either say, no, it's not, because they're inconsistent with the consistency conditions, or I don't know. And so in this mode of doing things, you can definitively rule out candidate spectra. And by using more and more consistency conditions, you can hope to find stronger and stronger bounds. That's the general idea. So if that ends the overview part of the talk. The questions.
I have another question, James.
Yeah,
at this point, have you used that you're working in dimension 2 already or not?
No, I haven't.
Okay.
So yeah, that's sort of one thing I want to get across, is that this approach is fairly general. It sort of works most easily and most nicely in 2 dimensions for the reasons that I'll say in a minute. But in this in this part where I talk about more bootstrap bounds, I'll show some results in general dimensions. But sort of so far, the most sort of the most impressive results have come from 2 dimensions, just because things simplify a lot for sort of obvious reasons. Yeah, but yeah, this idea is fairly general. Okay, so yeah, let me now say some of the technical steps for the specific case of hyperbolic surfaces. So how you would prove those bounds that I mentioned earlier, or how you prove the first one at least. So in 2 dimensions, it's nice that we have a complex structure. So we can use complex coordinates, ZZ bar, and in some coordinate patch, you can always write the metric so that the non-vanishing components are GZZ bar or GZ bar Z. So this is just like isothermal coordinates, but in using the complex notation. And what this means is that when we talk about components of tensors, we can always restrict to those with only Z indices, because I can always trade a Z bar index for a Z index using these non-vanishing components of the metric. So there's some isomorphism between these different spaces of tensors. Okay, and once I've done that, I can then, I will define the helicity of a tensor to be the number of upstairs Z indices minus the number of downstairs Z indices. So for example, this would be helicity minus 1. We can then define this a complex line bundle, which is the space of smooth helicity S tensors, where S is some integer. And on this line bundle, there's this inner product, which I'll make use of a lot, and denoted by these angle brackets. Okay, so we can define 2 natural covariant derivatives acting on these spaces of helicity tensors. One which decreases the helicity by 1, and I'll call it an nabla, and one which increases the helicity by 1, I'll call it nebula bar, and these are adjoints of one another up to a sign. And in fact, these are just the components of the ordinary covariant derivative associated with the Lebesgue connection in complex coordinates. Okay. And so, yeah, locally you could write them like this. And similarly, you can define two Laplacians depending on which order you act with these covariant derivatives. So this operator nebula is a linear elliptic operator. So for s greater than 0, I can orthogonally decompose the space of helicity minus s tensors in terms of the image of this operator nebula plus the kernel of the adjoint, which is nebula bar. So this is just an orthogonal decomposition, which must exist because it's a linear elliptic operator. And this second term here, this factor, is the space of holomorphic S differentials. So this means the tensors of helicity minus S, which are holomorphic. By the Riemann-Roch theorem, we know that the dimension of this space of holomorphic S differentials is a topological invariant. So I can write it in terms of the genus like so. So NGS is going to be the dimension of the space. And for S equals 1, which corresponds to holomorphic differentials, the space has complex dimension G. And for S greater than 1, it has complex dimension 2S minus 1, G minus 1. We can therefore introduce a finite orthonormal basis of holomorphic S differentials, which I'll call phi I superscript S, where this index I runs over the dimension of this space. And it's also useful to define the conjugates phi bar, which are the associated tensors of positive helicity. So in components can write them as complex conjugate times factors of the inverse matrix. So earlier on, I mentioned this orthogonal decomposition. I can combine this orthogonal decomposition of the space of helicity minus S tensors with the decomposition of a function in terms of eigenfunctions and a holomorphic S differential in terms of the basis of holomorphic S differentials to decompose a general helicity minus S tensor in terms of derivatives of holomorphic S differentials and eigenfunctions. So that's what this equation is supposed to show, where here I've defined phi I0 to be the eigenfunctions phi I, just so that I can write everything uniformly like this. And similarly, I define this to be the dimension of the space of eigenfunctions, which is infinite. So this is just like a transverse traceless decomposition, but in complex notation. So for example, if I, for some non-negative integer alpha, consider the derivative of a holomorphic differential phi I, and take the product with another holomorphic differential phi j, I can expand this in terms of derivatives of holomorphic S differentials, where the rank S is runs from 2 to alpha plus 2. And with the prefactors in this expansion are just the overlap of the this term. So you can think of this as like inserting a resolution of the identity if you want. So I'm just expanding in the spaces of derivatives of holomorphic S differentials and eigenfunctions. So earlier I defined these triple overlap integrals of 3 eigenfunctions. Here I want to generalize that to talk about triple overlap integrals of eigenfunctions and holomorphic S differentials. So given 3 eigenfunctions or holomorphic S differentials, phi I, phi j, phi k, with rank S1, S2, S3, where S3 is greater than or equal to S1 plus S2, I can define the following triple overlap integral. which I'll call Cijk superscript S1, S2, S3, which is just the overlap of these three eigenmodes involving the fewest number of derivatives. So remember, this inner product I can write as just an integral over the product of this term times the conjugate of this term with some factors of the metric. And the point of doing this is that it turns out we can write a general triple overlap integral in terms of these basic triple overlap integrals. For example, here I've shown this overlap of these two terms, which appeared on the previous slide in this numerator here. And if I write this as an integral, I can use integration by parts to reduce the number of derivatives until I get down to the basic triple overlap integral C. And it turns out this will give you the following expression. So I can write it in terms of this basic triple overlap integral with some extra factors which arise from the integration by parts and commuting of derivatives. And this star here is just because this is not exactly true, but it's for the purpose of this talk, it won't matter. There's one small exception. Now let me move towards how you derive these bounds on the spectral gap. So for this bound lambda 1 less than or equal to 3.83 ... What we're going to want to do is to consider a quadruple overlap integral of two different holomorphic differentials, phi I and phi j, which I can write in the following form. We now want to use the spectral decomposition to write this in terms of a sum over squares of these triple overlap integrals, where I use the spectral decomposition on each of the terms that are adjacent to one another. So using this decomposition here, where I replace the numerator with this expression in terms of basic triple overlap integrals, I can rewrite this quadruple overlap integral in this final form shown here. So it's some reasonably complicated looking expression involving the squared norms of these triple overlap integrals, C, with some prefactors that I can write in terms of gamma functions and so on. And so I'm summing over the holomorphic S differentials from with rank 2 up to alpha plus 2. So this is like a more complicated version of what I showed you in the beginning, where I rewrote this integral of product of eigenfunctions in terms of triple overlap integrals. Here, I'm just keeping track of all the extra indices that I have because of the fact that now we're doing integrals of products of differentials. But the same idea is the same idea. So I could alternatively write this the same quadruple overlap in the form that I've indicated here. So all I've done is swapped the positions of these phi j's. When I write this out as an integral of the product of these four things, it's trivially the same thing. But now I'm just going to use the spectral decomposition on the indicated adjacent terms. And when I do the spectral decomposition in this way, writing the quadruple overlap integral, I get the following expression, which only involves the overlap integrals with the eigenfunctions. So on this slide, I had overlaps with the holomorphic S differentials of higher rank, but in this way of writing it, I only have the overlaps with the eigenfunctions. And here I've defined these polynomials chi to be defined as so, just because they occur frequently. This is just two different ways of writing the same integral, so they have to be equal to one another. And by imposing this equality, I get some consistency condition. And so now you can see that this consistency condition is relating the spectrum of the eigenfunctions to the holomorphic S differentials. And so that's sort of where the non-trivial part is going to come from. Derive these consistency conditions for various values of alpha. So remember, alpha was just the number of derivatives I had up here. So I can find these consistency conditions for alpha from 1 up to, say, some integer j minus 2, and combine them all together into some vector equation, which has the following form. So here I've combined both the consistency conditions for distinct differentials with the consistency conditions for identical differentials. And so you get various products of these triple overlap integrals. But the precise form of this isn't really that important. What I've done is define these vectors f's. These different f's are just vectors of, so this is just some constant vector. This is a vector of matrices whose components are polynomials of the eigenvalue lambda k, which is being summed over. This f is just a vector of polynomials of lambda k, and these other f's are just constant vectors. But here I'm just combining all the consistency conditions together in some convenient form. The important thing is that these vectors always come with squares of these triple overlap integrals, or in this case, a more complicated inner product involving a matrix. How do we get eigenvalue bounds from this system of consistency conditions? The idea is to assume that lambda 1 is greater than or equal to some number, which I'll call lambda star, and then try and find a contradiction. So in particular, we're going to look for some constant vector alpha, such that when I dot alpha into this equation, I get something which leads to a contradiction. In particular, I'm going to try and choose this alpha, such that when I dot it into this matrix F naught prime, it's a positive semi-definite matrix for all assumed values of the argument of this, the polynomials that this matrix depends on. For all lambda k greater than or equal to lambda star, I want this to be positive semi-definite matrix. Similarly, I want alpha dotted into this vector to be non-negative. I want alpha dotted into the constant term, which was the term appearing with the factor of the inverse volume, to be equal to 1. That's just a normalization. And similarly, alpha dotted into all the other terms should be non-negative. If I can find an alpha such that this is true, then I have a contradiction, because dotting alpha into this equation, I get a strictly positive quantity plus non-negative quantities add up to 0, which is impossible. And therefore, I can conclude that the spectral gap must be less than this lambda star that I assumed at the beginning. So this is how you would find an upper bound on the spectral gap lambda 1. So how do you? Now the problem is how would you find a vector alpha like this, satisfying the system of equations? Well, this is a problem that can be reformulated as a semi-definite programming problem. And maybe you won't say too much about that, but for example, requirement that some polynomial should be non-negative for all non-negative values of its arguments. You can equivalently phrase that in terms of the fact that I can write this polynomial in some form involving matrices which are positive semi-definite. So that's where this comes in. Geometrically, you can kind of think of this as the question of if I hand you a bunch of vectors, is it possible for them to add up to 0 with positive coefficients? So I maybe should emphasize that we're using the fact that these norm squares are positive here in a crucial way. Ignoring this matrix term for a second, the question is, given some vectors, some known vectors, can they add up to 0 with positive coefficients? And depending on the vectors, this may or may not be possible. So in particular, if I can find a separating plane alpha such that the vectors fall to one side of this plane, then there's no way they can add up to 0 with positive coefficients. So finding an alpha is like searching for such a separating plane, at least in some of the more simpler cases. This is the sort of geometric picture that you can have in mind. Okay, but you can ask a computer to look for this alpha given the system of equations, and I use in particular this program called SDPB, which was written this physics problem, the conformal bootstrap, by Sim and Stuffins, and again this this is a non-rigorous implementation of semi-definite programming, but there exist more rigorous ones out there. And so using this system of consistency conditions coming from two holomorphic S differentials with this integer j equal to 50, so that's just telling me how many derivatives I'm including, which corresponds to 196 consistency conditions, I can obtain this upper bound on lambda 1 that I quoted earlier. So that's where the bound on the genus 2 or above comes from. And you can imagine doing more complicated things by considering systems of integrals of more than two holomorphic differentials. And that's how you can find bounds on surfaces of higher genera. Okay, so let me mention this maybe curious fact that comes up when you're looking at integrals of products of eigenfunctions phi I. So you get some similar system of equations. And the point is that there's some polynomial here, which appears in the term corresponding to the sum over the eigenfunctions. And these polynomials all have this, this is a vector of polynomials, and these polynomials all have this common zero at the arguments 3/16 and 1/4. So this is that 3/4 that I mentioned earlier is just the ratio of these two numbers. But this happens more generally. And this is, I guess, curious because this 3/16 is some number that appears in various places in spectral theory of hyperbolic surfaces. But I'm not sure there's I'm not sure what the deep reason is for that. So in the last few minutes, let me talk about some other bootstrap bounds. I talked about upper bounds on the spectral gap, lambda 1. You can also find bounds on lambda 2. So for example, here I've quoted an analytic bound. So you can derive this by hand on lambda 2 in terms of lambda 1. And in the plot here, I've shown the numerically optimized version of this bound. That's this upper line here. And you can see that it carves out this upper triangular region that we had before. And in fact, it falls in this region quite close to this family of genus 2 surfaces, which is the reason that I included this this black line, which shows that the bound is nearly optimal in this region. So that's another kind of bound that you can derive. Something else you can do is if you have some space which seems to saturate your bound, by plotting this polynomial alpha dot f0, you can sometimes also see the higher eigenvalues of that space. So for example, if you try to maximize lambda 1 for a system consisting of a single holomorphic 6 differential, then the bound you get seems to almost be saturated by this hyperbolic triangle, the 237 triangle, which is some special triangle in hyperbolic theory. So its eigenvalues are these indicated by these black lines here, the first two eigenvalues. And this blue curve is this function which you get from the solution to these bootstrap equations. And you can see that this function has minima precisely at the eigenvalues, at least for the first 5 or 6 eigenvalues. And so the idea is that the hope would be that in the limit we have an infinite number of consistency conditions, you would get some function which has double zeros precisely at the spectra of whatever space is saturating the bound. And so then you could read off the entire spectrum. So this also illustrates, so I've so far only been talking about closed manifolds, but in fact, everything I've said also goes through for quotients of closed manifolds by subgroups of the isometry group. So that's why you can get things like orbifolds or this triangle in this case, with Neumann boundary conditions, I should say. Okay, you can also do all this in higher dimensions. So here's the version of this plot of the upper bound on lambda 2 in terms of lambda 1 for hyperbolic D manifolds for D equals 2 to 6. You can also find bounds on the spectral gap of transverse traceless tensors. So this plot shows these lines are upper bounds on the spectral gap of transverse traceless rank 2 on a hyperbolic D manifold for D equals 3 to 6, corresponding to these different colors. as a function of the spectral gap on functions. And this is some kind of unusual shape. There's some bound, there's a finite bound except for this small interval down here. But that's just to show you the things you can do. Another thing you can do is find bounds on these triple overlap integrals themselves. Here I've shown a sort of semi-random example where if I assume lambda1 is this number, 0.948, I can find an upper bound on this triple overlap of phi1 squared times phi j in terms of lambda j. This blue bound is this blue line is the upper bound, and this is a log plot, so these have to decrease exponentially, in fact. And these black dots are just examples from some particular manifold, just to show you that they are close to the upper bound. And this dashed line is an asymptotic bound due to Sarnak and Bernstein-Reznikov. These triple overlap integrals are the analytic number theorists are interested in these because they have a relation to L functions. And so, for example, they've proved these sorts of asymptotic bounds on their size. And lastly, let me move away from hyperbolic manifolds and say something about retrievable flat manifolds. So I briefly mentioned that this approach can also work for Einstein manifolds. So for example, you can find this bound on the ratio of consecutive non-zero eigenvalues, which is true for Ritchie flat manifolds with special holonomy. And it's saturated by certain Fourier low values of these eigenvalues. Okay, so let me then conclude. So hopefully I've convinced you that this bootstrap approach can give you interesting eigenvalue bounds. There are lots of other things that might be interesting to explore with this approach. Here are just a bunch of semi-random ideas. So for example, you could try and say something about large genus, hyperbolic surfaces, try and look at fixed tensors on hyperbolic 3 manifolds, and then hope to find bounds on the spectral gap for 3 manifolds. And you could also look at Dirac operators or non-compact manifolds. So yeah, let me finish there, and thank you for listening. Happy to take any questions.
Thanks a lot, James, for the talk. I think we have time now for some questions. So if you have any questions, you can either ask them in chat or unmute yourself and just ask it directly.
So let me ask a question. Did you try to apply these methods in the Euclidean setting for boundary value problems?
No, I haven't, but that's sort of another thing that I have in mind. It'd be interesting to see if that works.
Because in the Euclidean setting, there exist various estimates on the gaps, on the ratios of eigenvalues. So it would be very interesting to see if your method could give something better.
This is kind of like this, what is it, Payne Polyer Weinberg? Yeah.
Mm-hmm.
Yeah, that would be, yeah, I could imagine it working, but I haven't like sat down and tried to do it. But it seems like everything is there for it to work, as far as I can tell.
Do you think these methods can be used to prove lower bounds on higher eigenvalues, like the Otal-Rosas bound, for example?
Yeah, I've thought about this a lot, and I think, as far as I can tell, that's not the kind of question that you're allowed to ask these consistency conditions. Because it can say, like, I hand you a spectrum, I can say this is not allowed. I think you can ask a question such that it would, of that form, give you a lower bound.
I mean, you could ask if lambda 2g minus 2 could be like a quarter or less than a quarter, and then get a contradiction possibly. And the reason I'm asking is whether you could prove multiplicity bounds in such a way.
Right. Yeah. I've also wondered about this. Yeah. Following on from your talk. I wanted to do this before, but I ran out of time. But one thing you could imagine trying to do is starting with some system of, say, like 9 eigenfunctions, which are distinct and have the same eigenvalue. And then you could hope that the consistency conditions just tell you that can't work for any value of the eigenvalue. That would be one way that you might try and improve multiplicity bounds. I think, yeah, you really have to include them as external states, because that's sort of that's where you're telling. But yeah, I haven't tried this, but I think that would be a sort of natural thing to try.
Maxim, for the question. Do we have time for questions if anyone have any? I was wondering myself, so in those other things that you want to explore with the method, for example, the large unit setting, what are the obstructions that prevented you from looking at them? Are there difficulties that appear in these situations? That
it's just a matter of developing the technology, really. I guess for two manifolds, it's easy to derive these consistency conditions for arbitrarily many derivatives. And that just comes down to the fact that the commutator of two covariant derivatives is simple. In higher dimensions, I just don't know a good way to derive these things when you have like many derivatives, at least so far. But that's not like an insurmountable problem, I don't think. It's just a matter of finding a clever way to figure these things out. To some extent, this representation theoretic approach that I mentioned by these other authors is maybe a good way of solving that problem. They think of everything in terms of representations of SL2R or SL2C in 3 dimensions. And, it seems like maybe it's sort of easier to combine infinitely many of these consistency conditions together in that language. But so far, that hasn't been worked out for 3 dimensions.
We may have time for one more question. Maxim, I see you've unmuted yourself, so maybe.
Do you think these methods can be used to prove sharp bounds that the Bolza and the Klein quartic maximize the lambda one, or does it always lead to a strict inequality?
Yeah, that's a good question. I'm not sure. I think okay, so let me mention one thing, is that at least for this system that I mentioned, it doesn't quite converge to Bolza. It converges to Bolza plus some fixed number. So here I'm showing the difference as a function of this parameter j. As I increase j, you can see it sort of exponentially converges, but then it sort of flattens off. So it seems like it for this system doesn't, even in the limit of infinitely many consistency conditions, it doesn't converge to Bolza. But the hope would be that if you include more information about Bolza, such as that it has some holomorphic quadratic differentials and so on, then you have larger and larger systems of these consistency conditions, and eventually you would hope that for some sufficiently large system it would eventually converge. But that's sort of unknown if it does in the end converge. There's a similar question in the physics context, this famous model called the 3D Ising model, and this approach has been used to find very sharp bounds on some numbers associated with this 3D Ising model, but it's not known if it really converges. So that's like an interesting question, but I don't know.
You have the same thing in genus 3?
Yes, yeah. It also, I guess I didn't make this plot, but well, I guess for genus 3, I don't know the precise value of the spectral gap. Find was this 2.678, I think, so 3 decimal places. But so yeah, presumably there it also the bound converges pretty quickly. So you did have to ask what's the actual value of the Klein quartic to high precision. But I don't know that.
Actually, I have a question for you. Is it known, like if Bolza is a critical point for lambda 1, just on the moduli space of hyperbolic surfaces of that genus? In fact, while we're at it, what's known about the critical points of lambda 1 on the moduli space?
I guess I don't know what a critical point
So take the variation of the eigenvalue with respect to the hyperbolic metric. There's a sort of standard formula for that, which would be Laplacian dot phi phi, where phi is the corresponding eigenfunction, and Laplacian dot would be a quadratic differential, holomorphic quadratic differential, and you would get yourself a triple product, but one would be a holomorphic differential, and then you'd have the eigenfunction appearing twice. So you would need that thing vanishes for all the holomorphic quadratic, all the tangent vectors at the Bolza surface to moduli space, and so forth. Bolza, yeah. Maybe there's some symmetries or something which force that to be 0.
Yeah, I've never thought about it in those terms. I know that it sort of achieves this large eigenvalue by things becoming degenerate at the point because it has a large multiplicity. So
Well, maybe you can use your technique to locate critical metrics for lambda-1.
Well, yeah, can you say again the condition? It would be that this overlap.
Well,
of
it's just the
holomorphic
standard
differences.
perturbation formula for eigenvalues. When you take the variation of an eigenvalue, so we're doing it with respect to hyperbolic metrics. You know, in general, when you take the perturbation for a one-parameter family of Laplacians, you get Laplacian dot phi phi, where phi is the associated eigenfunction. And Laplacian dot in this case would be, you know, a holomorphic differential. Metric, the variation of the metric is a holomorphic differential. So you get like a triple product where you have a holomorphic differential and you have phi squared. It's like the Feynman-Hellman formula in standard Schrodinger perturbation theory. But I don't know to what extent people have studied this specifically for hyperbolic metrics. I'm sure that Scott Walpert or somebody like that, Chris Judge, if he's still around, those type of people should have probably do study these things. You know, like on a round sphere, it's easy to find out what you know about lambda-1 being critical, you know, because you sort of forces the lowest eigenfunctions to define an isometric minimal immersion into a sphere. You know what I'm talking about? This goes back to Marcel Berger in the 70s, and there's like a whole world of people who study critical point structure of lambda-1. Somebody in the audience, I'm sure, knows about it.
Okay, yeah, I don't. Yeah, I guess I don't know much about it, but it's interesting that if it has this formulation in terms of the vanishing of this overlap, then that's something you could input into.
It sounds similar to what you're doing in some ways. Yeah.
Yeah, I'll look into that more. Thanks.
Thanks, Steve, for the intervention. Does anyone else have something to contribute today? All right. Well, thanks again, James, for the presentation today.